Let's do this then. Let us go to Mr. William Alek, who has been patiently waiting.
Hi, Tim. Okay.
Bill, yeah, are you ready? Take it away, man. Take it
I'm
away.
here.
I do not have an introduction.
Okay, share screen. Okay.
Thank you for presenting, Bill. I think Wayne will probably be here in a while. That's okay. We can push him back a little bit.
Okay. I assume everyone can see the screen.
Yep, you look great.
How's that?
Yeah. Oh, perfect. Perfect.
Okay. Okay, well, let's get started here. Basically, this is the culmination of almost all my work here. You know, I got into the field here back in '97. I went to a conference. Tom Bearden was presenting. He's probably, at that time, probably the most authoritative presenter on the subject. And he always spoke about scalar waves. And that was always a mystery to me. What is all the scalar wave stuff, you know, he's presenting here? And so really this really started my journey, you know, in this area. And so let's get right to it here. Okay. Okay, what is a scalar wave? Okay, Tom describes a scalar wave, or he also called it a pump wave, as a local gravitational wave. He describes matter as being trapped electromagnetic energy. Well, guess what? That's true. Okay, and I can show you in the quantum wave theory that what Tom spoke about, that matter, electrons, protons, it's all trapped electromagnetic energy. But it's set up as a counter-rotating waves. They're trapped waves that form a particle. And you have this scalar component associated with it. That's this, what Tom referred to as this local gravitational wave. Okay, so let's get into more detail here. To produce a scalar wave, Tom speaks about in his lectures, and his lectures are posted freely on the internet, where he goes into this kind of detail here. And it's the cross product of two charges. Well, we know when we try to force two charges together, you have to overcome what's called the Coulomb barrier to get what's called fusion, right? So you get into this opposing vector. And this also gets into this law of squares. And I know the serial technology talks about this as well. And there's also a movie that came out, I believe it was last year, called Tenet, where it gets into time forward and time reversed properties here as well. So you have this law of squares occurring with this phenomena of Q cross Q, okay? So in this technology, to see the scalar wave term appear, you need to operate your device in resonance. It has to be operated in resonance. Otherwise, you don't really see this property occurring, okay? Okay, so here's a picture of my test bench. And this test bench can consist of a sine wave generator. It's programmable sine wave generator here. This particular one here is made by GW Instec. And the scope that I'm using, and you want to use a scope like this because it's an isolated channel, 4-channel scope. And what I mean here is that each channel is physically isolated from its next channel here. In other words, there's no grounding between the channels. So you need to use an isolated channel scope. What you see here is the transformer, okay, that sets up this opposing field action, okay? And there's 2 amp probes, and I measure the voltage. And so the amperage is converted into a voltage, and that's what you see on the scope here. And you can see on that scope a very strange wave pattern. What you also see here is sine waves, but this very strange blue trace up here has the scalar wave function that Tom spoke about. Okay, now to get this to appear, you set up this transformer in resonance, which means that the output of the transformer is connected to a capacitor. Okay, so that your voltage and current will be at a phase difference of 90 degrees. Okay, and then up here, I wrote some software that basically reads the scope values and does some calculations. And I'll show you what those calculations are, because they compute all the, well, it not only displays voltage and current RMS values, but it also calculates what the phase differences are between the input and output, the reactive components, basically everything you need. The most worthless calculation it does is probably power factor. You don't really need that at all. But anyway, it figures out what the real power is. Okay, but when you operate in resonance in this type of mode, there is no real power associated. It's all reactive. Okay, so let's go on to the next slide here. Okay, so how to make a scalar wave. Now, Tom said in his lectures, any competent lab could do this. But when I asked him, I think right back around 2001, I asked him, how did he do this? He turned to me and looked me straight in the eye and said, "Don't you ever ask me that again." And it's like, whoa, okay, Tom. So it took me 20 years to figure this out. But anyway, I figured out what he was talking about, okay? So again, we're looking at Q cross Q, and that's the whole fundamental part of this scalar function, okay? And so what you have are opposing vectors of charges in this situation. And of course, Tom always said matter is made of trapped electromagnetic energy. And again, I'll tell you, that's absolutely true. Okay, that shows up in the quantum field theory. Okay, so let's continue here. How to determine resonance? Okay, well, here's the output of the transformer shown on the left. And the configuration is that it's set up as a bifilar, like coil output arrangement. And you'll notice the output capacitor here. And then, of course, later on, I attach a load, okay, to this output. And so what the transformer is doing is setting up opposing forces inside your magnetic material. Okay, then Tom also refers to this as like we're operating in this nonlinear type mode here. Okay, so we're producing an opposing magnetic motive forces. And so it's going to produce a scalar function. Now, the diagram on the right, where resonance occurs at minimum input current. So we have a resonant action here. And I tuned the output of the programmable power supply to this minimum input current that we see here coming into and powering the device. So we tune the device with minimum input current where it's at resonance. Okay, that's how you do this. So here's a picture of the transformer and capacitor arrangement here and how it's connected. And you see here towards the rear of this transformer is where we set up these opposing magnetic forces in this case. So the input side of this coil, you see on the left side, this is where we connect this to our programmable power supply. The output is connected this way, and it's set up in such that the voltages on the output they sum up, but the magnetic components, okay, we have them converging, okay, to set up our opposing field action. And we set this up in this resonance mode here. So next slide. Now, Tom also got into what are called PCMs, which are phase conjugated mirrors. And I'm still trying to wrap my brain around this. So personally, I don't have a clear understanding of what's going on here. But anyway, he sets up this pump wave action, okay, on your input side into this PCM. He calls this a nonlinear medium, and it outputs a time reverse wave. And so this is where we get into this time reversed action. And this is quite popular with the optics, and also I believe with sound as well, doing this time reversed outputs, setting up these replica time reversed waves. Now, what I think is going on in here is that the reactive component that you're seeing in that blue trace is, of course, the scalar wave. It's like it's something that's occurring in this magnetic material that is feeding out or reactive towards the output of this transformer. And that's what we see on the scale on the scope. So the input is inputting a current, and the transformer is sending back a reactive component, which is the scalar wave component, and the two currents they add, and that's that complex wave pattern with the three humps. And we'll get into that a little later here in terms of the detail. Okay, so this is a little bit more on the PCM wave function. Tom frequently spoke about this. Okay, so examples of these PCM resonators includes Tesla's magnifying transformer. And this is what I saw in his patents, is that Tesla was really transmitting scalar waves, in his output. The Floyd sweep device, the SQM, is space quantum modulator device, set up opposing fields. Stanley Meyer's water car that also used opposing field action. Just, you can see that in its patents. The Bearden Meg device, another opposing field action. Okay, in my transformer, the same phenomena. And in metamaterial resonators. Okay, you want to set up this opposing field action. And this is what I think was really behind the Hutchison effect. Okay, when he levitated these various heavy objects, like that 90-pound cannonball, doing his disruptive experiments on materials. I believe he was using various types of phasing, okay, and this opposing field action using radio waves. Okay, the physics of scalar waves. Let's get into that. All right, I was watching a YouTube video a few weeks ago, and lo and behold, I saw it. Okay, there's a scalar wave function inside of this quantum field theory. And then here it is, particles with mass. You'll see this function here of 2 pi f min squared. That is your scalar wave term. And I was stunned when I saw that. And it's for all particles with mass. Massless particles, such as photons, there is no mass with it. So that term is 0. But this term with the scalar wave term in it, squared, okay, this frequency can be 2 sine waves. Okay, a particle can contain two counter-rotating electromagnetic wave functions. There it is, okay? Counter-rotating wave functions producing the scalar wave term, okay? Okay, the mathematics of this. You will not find this in any textbook in regards to the Maxwell equations, which Heaviside minimized. And of course, Tom went to some detail about this. And this is really the failure of modern science, because what Heaviside did is that he took out the scalar component, okay, in the original Quaternion math solution of Maxwell's electromagnetics. But if you work with the original Maxwell electromagnetics, there it is. There's your scalar component. And really, this is all that you need. You don't really need Einstein's general relativity. You can supposedly do it with this Quaternion math solution here, because you have the scalar wave function that's part of this. And to get access to it is where you set up this opposing wave action, okay? And so what that does is that when you do that, this opposing wave action, in ordinary, the reduced Maxwell equations, you see that you have a zero vector, and that's it. Game over at that point. This is why you cannot mix electromagnetics with general relativity. It doesn't work, okay, because of this zero vector issue here and no scalar function. But when you work with the Quaternion math solution, and this is what Tom showed in his lectures, it's right there, is that you have this scalar wave component, the a squared term, plus the zero vector. And he called the zero vector this vacuum engine that's behind this. And behind the vacuum engine is the scalar wave function. Now, if we're using sine waves as our input, which we are doing, okay, with that sine wave generator on my test bench, you get the scalar wave term, which is a sine squared term. And so that's why when I saw this, the sine squared term is where I went back up to this video. And you can view, look at this video. This is a slide right off that video is where you have the scalar wave component. There it is, F min squared. So built into particles with mass is that you have the scalar wave term. So it's true what Tom Bearden said. All that electrons, protons, all that they're doing are counter-rotating electromagnetic fields that are trapped in that make up a particle. Okay, so here's the basic theory behind it, where you have the a squared term times the sine squared term. You have to have sine squared, which is the scalar component. Okay, the scalar wave inside the zero vector vacuum engine. And so Tom referred to the scalar wave, pump wave, okay, is a local gravitational wave. Okay, that's what he called it in his lectures. That's your gravity. Okay, so what does this look like? Okay, well, I modeled this in, I have an old version. I'm still running Windows XP because I still have the old software. It's all that I can afford, okay? But it's great for modeling. So the top waveform is what we're working with. Okay, the top waveform is what the sine wave generator produces. And so the transformer, the reactive component of this transformer is producing this scalar, the sine squared term. And so when I modeled that, this is what a gravity wave actually looks like, okay? It's this sine wave with the DC offset. So when you model this mathematically, you'll see a waveform like this. And then when you add the two together, okay, the input current plus the reflective, reactive scalar wave component from the transformer, you add the two, you get a waveform that looks like this bottom trace. And so lo and behold, that's exactly what we see here on this scope trace here. Okay, that blue trace on the scope is your scalar wave plus the current, okay, the AC current coming from the power supply. So let's go back up here. Okay, so that's what we see here in this third wave pattern, is the summation of the input plus the scalar waveform. And this is the actual scope reading here. The blue trace is your input current sine wave plus the sine squared term, okay? Okay, and then going back to the test bench here, kind of puts it all together, the software plus what we see on the Tektronix scope, the power supply here, transformer with the capacitor arrangement. Okay, so how do we determine all these phase angles and phase shifting that's going on here? Because it's got to be a hell of a thing to do for this Tektronix scope, is trying to figure out what the phase angle of this stuff, trying to calculate all this, okay? And so this is our device under test here, our DOT, okay, where we feed our input signal. Output is our resistive load plus the capacitor, which isn't shown here, but normally this is where we put our capacitor for this resonator. But anyway, this shows you the calculations that are involved, you know, figuring out what the cosine is, reactive power, apparent power, real power, you know, it figures all this stuff out for you, okay? And ultimately, you want to end up with knowing what the efficiency of your system is. Okay, so this is an actual output. This is a latest version of my software. You can actually go to my website and download this. Okay, you can download this for free. It mainly works with only this particular scope, this type of arrangement here. And, you know, I work with the Tektronix amp probes, you know, basically everything there is off the shelf, okay? And so we see here what the apparent power is, what the phase shift, the input phase shift, the output phase shift. In this case, it's resonating at a frequency of 400 hertz. And we see that we have two different, I calculate two different transformer efficiencies here because I want to make sure I'm close as possible to being on the mark, okay? So in this case, I have a load of 9.4 ohms on that transformer. And I see I have this efficiency of 90%, 89%, 90%. And that's unusually high, okay, for a transformer. Because transformers, when you don't operate them in this particular mode here, just operate as an ordinary transformer, they're generally between 75, 80%, maybe 85% tops. You know, but here we see a higher efficiency. And so I think that's due to the scalar component that we see coming from this transformer. So Tom frequently spoke about free energy, okay, with these type of systems. And I think we're seeing it here because there's this added force that we're seeing in this circuit. It's not just the normal electromagnetic forces, but we're seeing this scalar or this gravitational force that's also showing up in here as well. And that's what I think Tom means by, you know, this free energy. okay, is that we're seeing it as an increase in efficiency of this particular transformer. Okay, so what am I doing here? Okay, the software is performing all these types of calculations. So it's looking at apparent power, it's reading voltages and currents. And so it's going to do the apparent input power, the real input power calculation in watts. It's going to do all these type of calculations here, compute what the phase angle is. And that's a little mathematical operation here involving arc cosine, computing the apparent power on the output. And it's really computing all these. Probably the most worthless, output is power factor. What do you need that for, right? So anyway, we end up figuring out what the efficiency of this transformer is. And so I look at the phase calculations in regards to computing the efficiency, as well as the voltage and resistance, and computing the real power that way. And that's why I displayed the two. And it's less than 1% difference of 89%, versus 90%. But nevertheless, we're seeing this excess energy in these transformers. Okay, so this is some real outputs coming from the device here. And I'm mainly looking at the apparent power multiplier. And this type of transformer, it just has this extraordinary reactive power that comes out of this. And I'm seeing values as high as almost 11 times. If you look at just voltage and amps, okay, you don't really look at the phase shifting that's going on here. Even though the phase shifting is telling you that it's 90 degrees, 89.9, it's practically 90-degree phase shift, okay, with the capacitor. We see that we have these extraordinary voltage and amp outputs, okay? And then as you start to increase your load, okay, where it starts to impact the phase difference, okay? But anyway, I'm looking at mainly frequency, and I'm adjusting the frequency here and looking at this apparent power on the output here. Okay, so if we go back to the Bible here, one of my favorites is Luke 12:2. We're in a great revealing now, I feel, okay, where all will be known. Okay, that's what's happening now. Okay, and all this research, we're revealing the truth here, what's coming out, the great revealing. And that's what we're seeing, with this type of technology. Okay, so now we get into a very interesting area in regards to Tom's military applications revealed, okay? And Tom spoke quite a bit about militarizing scalar wave technology, and in particular, scalar wave interferometry, okay, for defense type applications. And to do that, you need two ground-based scalar wave emitters, okay? And what this does is that where the beams cross, okay, you have one scalar emitter over here, another scalar emitter over here, emitting waves, scalar wave beams, and where the beams cross, that little region creates strong electromagnetic field energy. And I always wondered what he meant by that. And it didn't really come out until I started looking at the mathematics behind this. Because in that region, it can destroy electronics. Anything that enters that region, okay, in a powerful scalar wave beams, anything that enters that region, you can have strong electromagnetic energy. Okay, so let's get into that. Okay, so we have scalar wave interferometry. And so this is what Tom spoke about years ago. And so we have scalar wave 1, scalar wave 1A and 1B. You can have destructive interference, or you can set up a virtual ground. Okay, that's set up in that region. Or just by changing the phase of those waves, okay, you can have strong electromagnetic AC. Okay, very interesting. And so this could be what's behind the Hutchison effect, is that, you know, he's using Tesla scalar waves to set up these type of interference patterns that can be very destructive. Okay. And so here's a diagram that shows a scalar wave interferometry. Anything that would enter that region, you can either set up a virtual ground or a strong AC potential, okay, in that region. And that's what happens when you mix scalar waves. Now, the question is, are the Russians doing this? Well, it's quite possible. You know, they could have their technology here. And I've heard of warships that all of a sudden lose their electromagnetics. Okay, the whole warship goes dead. Okay. And so there could be some scalar wave interferometry going on here used as a weapon. Okay, so that's pretty much the end of my lecture there. All my stuff is published. A lot of my stuff is published at academia.edu. Just look up under my name there. You can find a lot of this material. And that is my presentation. So you can look up intellect.com is where the latest research is on replicating Tom Bearden's technology, scalar waves.
Wonderful.
Okay, that's it.
Bill, thank you, sir. Thank you. 3:52 almost. So we're almost there for Wayne too. We're almost on schedule. So let's do this though. Before anything else, again, everybody, oops, side-by-side speaker. Bill, I'm gonna stop your sharing. Perfect. Okay, I'm gonna put this thing on gallery view. Everyone, please give Mr. Bill Alek a giant hand. Thank you. And I know that's kind of an update of a previous presentation you did. So thank you for sharing that with us, sir.
Yes.
Yeah, and thank you for your patience in scheduling also. You know, it's feast or famine around here, man. It's like,
oh, I know the feeling.
2 months ago, I was begging. I was like, please share something with us, you know, and then this month I've got people booked out 2 sessions. So, you know, but it's a good feeling. So let's do this again.